Okay, cool. So I can see in Slack that many of you have been working on the notebook and also raising interesting questions. Let me show you the notebook because there are a few things I want to tell you. Okay, first is that we are in a completely different area now. Think that in reality, you will be given data and you will be on your own trying to find possible patterns in this data. And of course, if you allow yourself lots of freedom, for example, remember like in neural networks, if you allow yourself to have lots of parameters, lots of clusters, lots of things, lots of ways to divide your data, you are going to find patterns that might not be there, might not be what you want to do. But in reality, you are going to be facing a situation where you have no guidance. So the idea is that when you start learning unsupervised methods, you don't do it just dwelling into the unknown. You actually check, use a known label to actually see how well you are doing. But that's artificial, right? That's not what will happen in reality. So I want you to keep this in mind. For example, when we plotted this thing here, this PCA projection into 2 dimensions, what this is doing is showing the points, data points, and how they distribute on those 2 dimensions. These are supposed to be the 2 directions where the highest correlations were present in the data. If you plotted the third one, it will mean that you are adding a tiny bit more information because you are adding not just the 2 highest correlation directions, linear correlations, but also a third one. And if you plotted a 4th dimension, which won't be able to visualize, you will be adding a tiny bit more information. So this linear transformation you are making, these correlations are really the important information you need. The more dimensions you add, the more you are going to recover the full information you had in your initial program. But the point of doing the dimensional reduction is precisely trying to simplify your problem and try to find 2, 3, a number of important directions and disregard the rest of the information. In the PCA, those will be linear combination of your initial data points or a fixed linear combination of your initial data points. Okay, and in this plot, what you see is that in reality, if you had asked for this data set without knowing any labels to actually display the projection in 2D, this is what we would have shown, but without the colors. So imagine that now, instead of having all these colors on top, I show you a plot, same plot, but all the data points are actually in black, same color. And I ask you to find features, sorry, not features, but to find patterns in this data. And you see, you might say, well, I don't know. So imagine all this is black, it's black color, the dots. I see something over here, which is a tiny bit separated from something over here. I see some density over here, some more density over here, but it could be the same cluster. And this seems to be a tiny bit separated from this other. I hope you can see my pointer, otherwise it doesn't make any sense what I'm saying. But
Yes.
okay, thank you. But you see, I displayed not just what the PCA gives you, but also what the true labels are, because I know them. Okay, but that's a trick. No, I'm not tricking you. I'm trying to tell you that precisely. If you just looked at this by eye, or then you ask some criteria of clustering based on distance and density, most likely you will not find 10 distinct clusters, as for example, a supervised learning will learn quite quickly. Okay, so this PCA projection is very simple, but it doesn't give us a representation that is a clustering enough. And that's why we need TSNE. When we do that, the same procedure now instead of BCA using another algorithm, which is the neighbor algorithm, gives you this plot. In two of the main components, so the first two main components for this dimensional reduction, when you project all your data, you get this. And you see, again, think on reality. If you do this with real data that you don't know anything about, but the output will be this, but without the colors. And you see, here you start seeing a clear cluster here, clear cluster here. There is some clear cluster here and so on. You see clustering appearing like in a much more clear way, more distancing among the clusters. So adding this locality into your analysis has helped, but it's not a silver bullet. You guys can still see that where you know that here they should be ones, they are very close and almost continuous to 8s, and there is some leakage you want on 9s near the 7s and the 1s and the 8s, and there is some leakage here you want of 2s near the 8s and stuff like this. So this is because we know the labels, we are checking what this cluster is doing, and we see that this dimensional reduction is doing better. It's better, it's not perfect, and that nothing is going to be. So if all this was black, and you were asked by AI to assign clusters, you would say, okay, there is a cluster here, there is a cluster here, this is a cluster, this is a cluster, there's something here, I'm not sure it's a cluster or new cluster or is close to this one. This may or not be joined with this other one and so on. So you see, it's not a silver bullet. Okay. So then you go and do exactly the same in 3D, thinking that maybe this here or the fact that the purple and red are overlapping each other could be separated if we were in 3D. And you go to 3D and you see that this is not necessarily the case. In 3D, you don't get those points that were overlapping or leaking from one place to another is not doing much better. Okay. So whether you run your clustering on 2D or in 3D, you are going to probably get a very similar result. And this might be different for a different data set. It might well be that your data set that you started with is super complicated, then you do dimensional reduction, and then you get to a point where doing a two-dimensional or a three-dimensional reduction, there's a huge difference because your problem is more, it can be reduced more genuinely to a 3D versus 2D or vice versa. But since the meaning of these directions is not straightforward, it's not like when you see a data set and you know nothing about this data set, you have an intuition of whether just adding more dimensions is going to help you, or is actually going to produce artificially more clusters than they should be. And again, there is yet another level, because this was just data visualization. We still need to apply a method of clustering, with k-means being a method just based on distance, but there are other methods that have been more sophisticated and so on. And some will give you features that the others are not able to be able to obtain. And now I also gave you this accuracy, but think of what we are writing over here. What we are doing is saying, well, so when you do k-means over here, let's say that I even tell you that there are 10 clusters. So I'm really guiding already the choice of clusters. It will separate all this data in 10 clusters. Again, remember that the real data doesn't have colors. You don't know what they are. what you know is that it's going to separate this data that you have visualized in 3D or in 2D into 10 clusters. It does this clustering, and then later on, we decide that we are going to check whether the clusters it assigned really corresponds to all twos, all threes, all fours, all fives, all six, and to what extent that is true. And what we see is that it does it to a 94% accuracy. But this is because I told the K-means to find 10 clusters. And with that guidance, it was able to then assign the twos to the 2 cluster, 3 to the 3 cluster, and so on. For the, let me go back here. Where is it? For the algorithm, when it does the clustering, it just, if you ask for 10 clusters, it will give you 10 clusters, but it won't know that the first cluster it finds, it corresponds to, let's say, 4s, or 3s, or 2s, or 1s, or whatever. It is, in order to check, that's why we had to do this mask over here, to make sure that the algorithm identifies that cluster number 1 corresponds to 4, and so on. And only in that case we can ask an accuracy, where the accuracy is respect to the true label that we know in this case. Okay. Now, in reality, you will have your data set, and you might not know how many clusters are a good choice. And there are lots of criteria on how to try to find the optimal quote-unquote number of clusters. And I wanted to show you one of these criteria is here. It's called the inertia. And the idea is that you compute these things about using k-means with a variable number of clusters from 1 to, here I put up to 20. And the criterion is very vague, is that when you see a drop in this inertia and then it stays more or less constant, that point in the number of clusters is the best point is the best clustering number. Now, here we don't see this at all. In our data, especially using PCA, remember that this is doing PCA, it sees that as it increases the number of clusters, it's going down and down and down, and you don't see like suddenly this drops. If we then plot this for k-means, but apply to this kind of projection, we are going to see something that is more steep. And indeed, around something bigger than 10, because you see here there seem to be more than 10 clusters, it's going to drop and then stays more or less constant. Okay, so what this means is that although we are trying to gain intuition of what works and doesn't in a problem we understand, we actually know the true labels. Criteria like this one of the inertia is going to be rubbish if your dimensional reduction is rubbish. And even when it's not rubbish, let's say like in this case, where you actually see clear clustering, it's not going to be perfect either, because you're going to have that the best, let's say the sudden drop will happen near 10, but it's not going to be exactly 10. So answering the question of Steve the other day, I didn't get a name, but was talking precisely about doing this problem unsupervised and whether we would learn that there are 10 clusters. And I told the student that you will have to inform that into your clustering method in order to obtain good results. And that's what happens here. Okay, so it's I guess we've been doing supervised learning, and we've been doing neural networks, which are very impressive, very precise, quickly arriving to a very high precision. They can deal with lots of variability in the data, and they can generalize well if you do your learning appropriately with very clear methods of regularization, dropout, doing data augmentation to make sure that your algorithm is more robust and so on. There are very clear ways of going when we are talking about supervision in learning. But when it's unsupervised learning, we are talking at a more qualitative level, and in which, for example, the clustering method that will work, quote unquote, is not determined at the beginning. Like this plot, I show you the different results from the different clustering methods, like affinity, k-means, and so on. Okay? And that's something we had to deal with. Now, somebody, I think it's called Fernando, yes. Fernando did something interesting. He then called k-means with 100 clusters. And Fernando, you want to explain what you did? So I'm not talking all the time.
Hello, can you hear me?
Yes, I can hear you.
Okay, I wasn't sure if we. So what I did is I did with the TSNE method.
Very good. Yeah.
So so basically what I did is I took for instance 100 clusters instead of 10, and I had a look at what the accuracy was, and I defined accuracy as so you take one cluster, you identify 100 clusters, and then you look for the mode, so which is the number that appear the most, and then this is how you label your cluster. So in some sense, here what I'm doing is I'm including some supervision, because I'm telling the cluster, I'm labeling the clusters. So this is something that you cannot do in unsupervised. And then I found that I got to something like 99% accuracy.
On what task?
Sorry?
So you got 99% accuracy on what task? What is the task?
So the task, what do you mean with the task?
Yeah, so when I say I get, let's say 90% accuracy, is in a task. Of, for example, I'm going to identify cancer cells, or I'm going to find new physics in an event. What is in your case, in what you've done, what the 99% accuracy is in what task?
So what I do is so I have the 100 clusters, then I label them. I label all the numbers there, all the pictures there by the mode of that cluster. So I'm saying in some sense I have multiple clusters that will be labeled as 2 and multiple clusters that will be labeled as 4. And then I compare the real value with the value that from the cluster that it corresponds to.
So you have about, let's say, 10 clusters per number.
Something like that, yes.
And when you have a new image, this image will go into, let's say if it's an image of a 5, it will go into one of the 10 clusters of 5 with an accuracy of 99%.
Exactly.
And that's very good.
Exactly.
So is that the task? Is that the task you would like to do?
Well, I mean, it's not exactly what we were trying to find here, because here we were trying to find that there are really 10 clusters or 10 categories, but it's kind of it's supervised here, right? Because
See, but let's say, as the student was asking, imagine that I just give you images, and I want you to find I want you to find that there is some clusters there, and then the next time I give you an image, you can put it in the right cluster. And what I'm asking is whether, and yes, you can only answer that question by looking at the labels, so by using some level of supervision. Totally agree. But I think what you obtain is really good, and I really want people to think about it. Good in the sense that is the typical pitfall that you will end up you do on supervision. So you have lots of data like we have here, and you start finding features in it. If you then do a large number of clusters, you are going to be able to, you are essentially modeling lots of patterns, right? The more clusters, the more patterns you are finding in the data. So likely what is happening is that, for example, when people write fives, sometimes they do it like this, sometimes they do it in some other way that is slightly different, and so on. And your algorithm is able to find clusters of behavior of when people write fives, twos, and so on. It would be interesting to see how many clusters you have of the number 8 or number 2 or number, because, for example, the way you write 0 is quite clear, but maybe the way you write 2 is not, or 7. And some of those lead to more clusters. Okay. And the other thing that that could happen as well in what you've done is that you then take this clustering and apply it to another larger data set, and it does not generalize well. So you are essentially the equivalent of overfitting, because you are finding many patterns in your data which should not be there. So this is really good. I'm glad that somebody took that limit. Yeah, Fernando?
So it's something like someone writes a 5 in a different way that is not in the previous data set. Maybe because you have so many clusters, it cannot identify it correctly or something like this.
Exactly, because it didn't learn, if you want, to be rough enough to really focus only on rough things, as the CNN will do, which just cares about, relative distances and so on. So it's probably going to generalize worse than as something that is rougher. So that is very good, because you see there is a compromise between level of clustering you do, how many you do, how many patterns you try to explain, and how much you might be fooling, quote unquote, not you, but in general, one is fooling oneself, thinking that, there are so many interesting features going on. And that's why I was asking you about the 99%. If your task would have been what the student proposed, which is if I give you the means data set, can you correctly classify numbers as in the 10 categories? Your procedure will have a very low accuracy, because actually every time it sees a 5, for example, sometimes it goes in one cluster or another. So the accuracy will be low. But on the other hand, because you have added so many features, not of features, patterns, then you are able to actually, you have many classes of 5, and every time you see a new 5, you are able to put it in one of those classes that are, for example, on number 5. So this is really good too.
So can I ask a question?
Sure.
So would it make sense to do some kind of hierarchical thing in which you go from, let's say, 100 clusters and then work on those 100 clusters to try to find correlations between them so that you eventually, does this make any sense?
Yes, absolutely. And in fact, it's something that the experimentalists among us will know about, because this is precisely when you do, for example, jet physics, that will be the way you do subjet analysis. You see a big cluster, or separate the jets into big clusters, and then you go into the clusters and find clusters inside the clusters, and so on. Or you do the other way around. You find mini clusters and then you merge them and so on. So yeah, this is an analysis that totally makes sense. I'm sorry, somebody was talking and I interrupted. No? Oh, there was also there were some good comments about the number of dimensions. I already said that sometimes having 2 dimensions, 3 dimensions, depending on your problem, it might lead to sorry, let me start over again. What I was telling you here is that in 2 dimensions you already see clustering, and it could be that for your problem, going to 3 dimensions will help, because some of these things that are overlapping in 3 dimensions, they do not overlap that much. So there, in 3 dimensions, your algorithm will perform better. But sometimes it's the opposite, because your problem is truly 2-dimensional, and by putting it in 3 dimensions, you are going to kind of start making your data to look a bit more complicated than it actually is. So there is not like a clear-cut definition of 2 better than 3 or vice versa. That's why it's good to first do an analysis where you actually know the labels, because this way you gain intuition. The same as for the gyroscope problem, they given you the data and also the labels, so that you can also learn from the intuition you gain from that. And I don't know if any of you guys have tried this one and want to
work a little bit with that, with the HAR, and it's interesting because if you do the TSNE projection in 2 dimensions, I cannot show it to you, but it's very interesting because you obtain, I mean, without looking at the colors, it's very clear that you had 3 clusters, and curiously enough, in each cluster you find a different type of activity. For example, there is one big cluster where you have different types of walking, one cluster where you have people sitting or standing by, and one cluster of people laying down. So it's kind of interesting. Then if you try to do the analysis with the k-mean, then you obtain an accuracy up to 83%. This is reducing to 2 dimensions.
This is, you said you see 3 clusters, but the number
sorry,
of
this is using 6 with all the activities, because the original data set is with 6 activities. But another comment is that looking at the projection in 2 dimensions, it's pretty clear and it's quite interesting. I will post it on the Slack so everybody can see it.
Or you're able to share your screen, I guess.
I don't think so. Let me check.
So you go on this button. I can stop. Let me stop sharing mine, just in case.
What do I do?
So on the right bottom, you see the bubble of speech, then the people, and then there is this arrow.
Yes.
And if you click on it?
No, I cannot. Only moderators.
Participants don't have privileges here, Veronica.
It's a bit, I had set up the session so that participants can share, but it doesn't work. Okay.
Veronica, you can become him presenter with a dot near his name, and then he can share.
So Roberto, aquí, here, attend the controls, make it a presenter. Thank you.
Okay. I can.
Thank you. Whoever told me, thank you.
Okay. Where's this? Okay. Okay. Can you see it now? Is this working?
Yes.
Okay. Yes, it is.
Yes, it's working.
Okay. So you see this plot?
And those are the 3 clusters and
yes.
the activities?
So, okay. Step by step. So in the data set, you have many data concerning this gyroscope, many different accelerations. There are actually 561 features. And the labels are these activities. So walking, upstairs, downstairs, sitting, standing, and laying down. The thing is that with just the principal component analysis, they're quite overlapping. And you would say that there are kind of 2 clusters. But then if you do the TSNE, Now, from 1 to 3, we have the walking activities. And you see that they are this kind of cloud of little clusters. On the other hand, the standby activities like sitting or standing form this cluster here down. So, and this is laying down. So I thought this was quite interesting because even without the colors, one could say that you have at least 3 different regions that are quite well separated.
Mm-hmm. And they do correspond to intensity of activity.
Yes, all these 3 colors, 1, 2, 3, correspond to 3 different kind of walking, as you can see.
Yes. 4, 5
then
sitting
4,
standing.
5 are sitting, standing in an anyhow upright position, and they form this cluster over here. And then laying down forms this cluster.
That's interesting, this too.
Yeah, and with 2 dimensions it's much better than 3, then you cannot really say much. And this maybe reflects to the accuracy, because if you do then the clustering with the 6 categories with 2 features in 2 dimensions, you get 83% of accuracy, while with 3 components, so in 3 dimensions, you get to 70%. You have a drop.
You
So
see,
that's
so
it.
that's no, that's good. It's an example of a real life example, I say, where going for higher dimensions is not helping. So it's really good. Okay, any more comments, questions? If not, on Monday we'll talk about reinforcement learning. Okay, see you.
Bye.